All right. Hello, everyone. Again, welcome. We're having a discussion. This is a discussion topic about a heavy lift drone. We're talking about the autonomy of the drone autonomy, not the pilot autonomy. And we were working through some math and simply ran out of time. So this is really sort of part two of that discussion, where I'm going to show, here's the Montrose Airport. He will be here right above the airport. He'll go up in the air to here. At this point, he'll be 5,000 feet above ground level. He'll make a right turn and bring himself all the way around like this at 125 miles an hour and bring him into position to do a final approach. And he'll come back and land at the airport, traveling about 18 miles, probably in 10 minutes, using up 20 pounds of fuel. Now he has inside that's an experimental drone, so he has inside of it 1,000 pounds of sandbags as a payload and 600 pounds of fuel. And again, this is part two. We're going to go back to a PDF, but I have to get myself to materialize first. And we are not going to discuss nose gestures. I'm just going to use that same procedure again since it seemed to work. And we'll see if I can materialize myself. And again, I've labeled this title of this video as Heavy Lift Drone Autonomy Discussions Part 4. It's a follow-up of Part 3. And this is a military thing. We've got some places around here in Colorado where we're going to do some work testing various parts of the drone. Taylor Park Trading Post. We're going to be going there, and we're going to go over here to Prospect Mesa. Just working out what the drone can do and what it can't do and what's a good idea and what's a bad idea. And I had him, not only did him flying it as a test pilot, but they might, if she wants to, ask one of the female test pilots, or military aviation, fully qualified combat aviation pilot, if she would like to do a 4-month temporary duty to this area to work on this drone. The point of it for these military pilots is to help the people creating this drone to give it the proper specifications. I think it should be a consortium effort. I know LinkedIn has all these venture capitalists. They need to make a consortium of Lockheed and Northrop Grumman for the plane, for the money, for the overall management, de Havilland to create the aircraft, Parker Hannifin for the pumps and motors to get the propellers going, and Rolls-Royce. Rolls-Royce is going to put the engines on it. And we were on this PDF. Again, the original plan of the drone was it would go straight up over the forward operating base because that airspace was safe, and then it would fly off. But I think they're going to go up for 10 or 30 seconds and then get themselves into fixed wing. They'll go up for 10 or 30 seconds with VTOL and then get themselves into fixed wing as soon as they can, because fixed wing is so much more efficient with respect to fuel. And we're going to go back now and take a look at that PDF. The other thing we like to do, of course, I like to say hello and welcome. I'm glad you're here. I do have a YouTube channel. I invite you to subscribe. I think you'll enjoy it. I try to put these videos on YouTube, and I refer to these videos at my website. I have links at the website to the YouTube videos. This is my website right here, and the page that we're talking about is this one. It's on the menu. You go to discussions not about a piston robot, and then you go to heavy lift drone autonomy discussions. That's where it is. And of course, I always like to put in this is a big heavy drone, but the simple truth is any physically real object has the potential that it might hurt somebody. And if you are managing a physically real object, it is my advice that you should manage it in a manner that is legally allowed and reasonable and safe. And if you can't manage it in that way, my advice is do not create it as a physically real item. All right, and so we're back at the PDF, and the engines are making 5,939 pounds of thrust. And we're going to use tilt rotor. The drone has tilt rotor. It's going to tilt the rotor so that some component of the thrust is vertical and some component of the thrust is horizontal. The vertical component of the thrust is 5,700 pounds. So the drone is 18 feet above the runway, right at the end of the runway, and it's making 5,700 pounds of vertical thrust, and there's 239 pounds of horizontal thrust left over to push the drone. Now, this is with amount of tilt rotor. I think they're probably going to tilt 2 or 3 degrees. I'll show you. There's a web page, and we will see if I can get through this. I may have to make a third video. And so here is this calculator, and we went to physics, and we did force, and this converts all the units for you so you don't embarrass yourself. Well, let me rephrase that. So I don't embarrass myself. I get this. It's just so easy to mix yourself up. And this is mass as weight, but it's okay. You can do it that way in the American system. So we have a mass of 5,700 pounds. Oh no, we're not calculating for F. We're calculating for acceleration. So we have a force of 239 pounds acting on a mass of 5,700 pounds. And it tells us that the acceleration will be 1.35 feet per second squared. And that is what I have here. The problem is this is not quite right because of the issue associated with drag. And the specification sheet for the de Havilland DHC2, and I of course understand with a computational fluid dynamics CFD program, you can get very accurate numbers, but you also need very accurate dimensional drawings of the DHC2 aircraft. I created in my 3D drawing program a reasonable, accurate drawing of the craft by copying the drawings that are available on the internet, but that's not going to be, I don't think, good enough for computational fluid dynamics. So we're going to do it this way. De Havilland lists that the best cruising speed based on miles traveled as a function of gallons of fuel burned is for it to run at 125 miles an hour. And when this plane is running at 125 miles an hour, it needs 300 horsepower to do that. And so I made this statement: if 1,001 horsepower, 1,701 horsepower is 5,939 pounds of thrust, then 300 horsepower is 300 divided by 1701 times 5939, which is 1047. So at 125 miles an hour, the drag on the plane is 1,047 pounds. Of interest, drag is proportional to the square of the airspeed. So if you change the airspeed by 1/2, it changes the drag by 1/2 squared. So at 60 miles per hour, the drag will be 1/2 squared, which is 1/4, times this 1047. So the drag at 60 miles per hour will be 262 pounds. Using the same logic, 30 miles per hour is 1/2 of 60 miles per hour. So the drag at 30 miles per hour will be 1/2 squared times the drag at 60 miles per hour, which is 0.25 times, this is 1/2 squared, times 262, which is 65.5 pounds. And at 0 miles per hour, we will set the drag at 0. I made a stipulation that we will do drag averaging. So from 0 to 30 miles per hour, we will take the drag at 0 miles per hour plus the drag at 30 miles per hour and divide it by 2 to give an average of 32.75 pounds of drag for that activity going from 0 to 30. 32.75. So the average of the drag going from 30 miles per hour to 60 miles per hour will be 65, which is the 30 miles per hour drag. Excuse me. 65 is the 30 miles per hour drag, and 262 is the 60 miles per hour drag. You add them together and divide it by 2 and get 163.7 pounds. Finally, going from 60 miles per hour to 125 miles per hour, it will be the drag at 60 miles an hour plus the drag at 125 miles per hour, added together, divided by 2 to get 654 pounds. That is this drag averaging thing that I did to solve the problem of drag. And now we're going to recalculate our forces, but allowing us to add in the drag effect. And there is a similar way of thinking that we have to use for the issue of lift. And I can just see that this is going to be more than 15 minutes, but I don't mind. I'll make another one. I guess I'm going to I'm going to find out. LinkedIn might say, "Hey there, Dr. Ray, you got to kind of chill it out a little bit." We'll see. Who knows what they're going to say? But I'll go through. I think it's interesting, and it should be done this way. So from 0 miles per hour to 30 miles per hour, available thrust is 239 pounds, but the drag, the average of the drag is 32.75. So the horizontal force available to push on the drone for horizontal acceleration is 239 pounds minus 32.75 pounds, which is 206 pounds. Remembering that the device is making 1,701 horsepower, and a lot of its output is still existing as 5,700 pounds of vertical thrust, keeping the drone up in the air. Using that same F equals ma equation that I just showed you, you get 206.25 pounds acting. And then I'll give you another calculation thing that I should show you. And that comes to this one, where you go to physics and you go to a uniformly accelerated motion and you ask for time and distance giving your starting values. And using that, instead of 239 pounds, we have 206.25. The acceleration becomes 1.16 feet per second squared. So we'll go back over here. So we're starting at an initial velocity of 0. 60 miles an hour is 88 feet per second. So 30 miles per hour is 44 feet per second. The acceleration is 1.16 feet per second squared, and we calculated. And what it tells us is, in this situation, the drone sitting 18 feet off the ground, nice and stable, no vertical activity, will travel 834 feet down the run. The drone is not on the runway. It's very important. This is the whole point of this airplane. It does not need a runway. And it's got 1,000 pounds of payload in there. It travels 834 feet down the runway. It takes 37.9 seconds, and now it's going at 30 miles per hour. What's interesting is it also begins to develop lift because it has an airspeed. All right, well, she wrote down on an index card lift, and she put her wristwatch on the index card and lifted it up and started flying around with her watch on it. That says to me, I'm out of time. I'll make another one. We will see how this goes.